Did you know that there is a tree whose leaves all grow in the shape of right triangles? It's called a trigonometry. You're welcome. All right, number one, simplify the expression using trigonometric identities. So we're going to need to know some trigonometry, but we're also going to need to know some math. So when I look at 1 minus secant theta times 1 plus secant theta, I think to myself, hey, I betcha I could just use the distributive property twice. Sometimes people call it FOIL, but I could multiply these two binomials. See what I get. 1 times 1 is 1. 1 times secant theta is secant theta. Then negative secant theta times 1 is negative secant theta. And then negative secant theta times positive secant theta is negative times positive is negative, and then secant times secant is secant squared. And then I get a plus secant theta and a minus secant theta that cancel out because secant theta minus secant theta is 0. And so that simplifies to 1 minus secant squared theta. Now, I need to use one of my fancy trigonometric identities. Which one should I use? Here's these Pythagorean identities. Here's one that has secant squared theta in it. Let's see, can I somehow make this look kind of like this? Well, let's see. If I were to subtract secant squared theta from both sides of this equation, I would get 1 minus secant squared theta plus tangent squared theta equals secant squared minus secant squared is 0. So now I got this part right here. I just need to get this off of this side. So I can subtract tangent squared theta from both sides. And I get, see, 1 minus secant squared theta. That's 0 equals 0 minus tangent squared theta. That's just negative tangent squared theta. So I multiplied out, simplified, and got 1 minus secant squared theta. And then I did a little bit of algebra on this Pythagorean identity to realize that 1 minus secant squared theta is equal to negative tangent squared theta. So that, my friends, is B. Simplify this expression using trigonometric identities. Well, let's see, I got sine on the bottom and I got cosine squared on top. If I'm going to be able to simplify, I'm either going to, if I start turning stuff into tangent here, what would happen? Well, it's harder to break apart a denominator than it is to break apart a numerator. So we don't want to go that direction, but cosine squared, I can use a Pythagorean identity to turn cosine squared into something that has to do with sine squared. If I subtract sine squared theta from both sides of this Pythagorean identity, I get cosine squared theta is equal to 1 minus sine squared theta. So let's see what happens if I replace cosine squared theta up here with 1 minus sine squared theta over 1 plus sine theta. Now resist the urge to try to cancel something out here because we have subtraction on the top, addition on the bottom, and this fraction bar means division, and we can't cancel out addition or subtraction with division. We have to cancel out multiplication. But what's nice is that 1 minus sine squared theta is a difference of squares. Just like in Algebra 1 when you factored x squared minus y squared, and that was x plus y times x minus y. Same thing happens here. This factors into 1 plus sine theta times 1 minus sine theta. And actually, you saw in the last problem that that we actually went in this direction. We had, let's see, what did we have? We had 1 minus secant theta times 1 plus secant theta, and when we multiplied it out, we got a difference of squares, 1 minus secant squared theta. So here we just went in the opposite direction. And it's nice that we did that because now we have a 1 plus sine theta, that's a factor of the top because it's multiplied. And we have a 1 plus sine theta that you can consider to be a factor on the bottom because 1 plus sine theta times 1, your 1 plus sine thetas will cancel out and you're left with 1 minus sine theta over 1, which is just 1 minus sine of theta. So peeps, that's A. Ooh, if cosine of A is 12 over 13 and sine of B is 4 over 5, and both A and B are in quadrant 1, then what is the value of sine of A plus B? Okay, now remember that sine and cosine are main trigonometric functions, came from right triangles. So if we think about a couple of right triangles that are in quadrant 1, and let's say this is angle A, then cosine of A is adjacent over hypotenuse. So that means this would be 12 and this would be 13. And that means since it's a right triangle, this is one of our pattern right triangles. That's a 5, 12, 13. If you didn't remember that, you could have just done the Pythagorean theorem to figure out that this side is 5. So if cosine of A is 12 over 13, then sine of A is opposite over hypotenuse, 5 over 13. So I'm going to make a little note here that sine of A is 5 over 13. And then if we look, and why is it important to say that it's in quadrant 1? Well, if it wasn't in quadrant 1, then it might be like this, and then the sine of A could be negative 5 over 13. But since it's in quadrant 1, we don't have to worry about the negative case. So there's this other triangle. Change my ink color. There's this other triangle that has an angle B whose sine is 4 over 5. So we got this right triangle, here's this angle B. The sine of B is 4 over 5. So sine is opposite over hypotenuse. So this would be 4 and this would be 5. This is another one of our special right triangles as a 3, 4, 5. And if you didn't remember that, you could have, again, done the Pythagorean theorem. And so let's see, if sine of B is 4/5, then what's cosine of B? Cosine of B is adjacent over hypotenuse, so 3/5. So why did I do that? Why is that important? Because if you look in your trig identities for sine of A plus B, it's this guy right here, you need to know sine of A and sine of B. You need to know cosine of A and cosine of B. So sine of A plus B is equal to sine of A times cosine of B. So sine of A is 5/13 times cosine of B, which is 3/5, plus cosine of A, which is 12/13, times sine of B, which is 4/5. And now I got to multiply first, then add. So 5 times 3 is 15. 13 times 5 is 50 plus 15, so 65. 12 times 4 is 48. And then again, 13 times 15 is 65. And now it's a good thing that we said it was in quadrant 1 and that these were both, so that 4 and 5 here were both positive. So I know that these are both positive, and I'm adding these numbers together. 48 plus 15 is 63. So sine of a plus b, and if you want to visualize what sine of a plus b is, all you would need to think of is take this angle A and add it on right here, and now we're talking about what's the sine of this big old angle right here. So sine of A plus B would be 63 over 65. And that, my friends, is A. Alright, how are we going to simplify this? Well, the thing that jumps out to me first is that I have a cosine squared in both terms. So I'm going to factor that out. Cosine squared theta times, what do I have left? Sine squared minus 1. Alright, well, does this help me? Sine squared of theta minus 1 is, let's see, here's sine squared theta, and if I get rid of the cosine squared theta, so subtract cosine squared theta from both sides, that'll give me, I'm going to move up here and do it, that'll give me sine squared theta equals 1 minus cosine squared theta. Well, that's not exactly what we got up here. Sine squared theta minus 1, if I were to subtract 1 from both sides, I would get sine squared theta minus 1 equals negative cosine squared theta. So I can plug the negative cosine squared theta in place of the sine squared theta minus 1. So instead of sine squared theta minus 1 right here, I'm going to plug in a negative cosine squared theta. And then positive times negative is negative. Cosine squared times cosine squared is cosine to the 4th theta. And that is C. Alright, take a little break. Go get a bagel or something. Do some push-ups, some sit-ups, run around the block, drink some water, and then come back and watch the next video.